Hello, everyone. Let's go ahead and pick up where we left off with a quick recap of momentum up to this point, and then we'll plow forward with the starting with the example that we didn't quite get to in the last class. So what we're going to do is we're going to be looking at momentum again. So momentum is, by definition, is mass times velocity, and we saw that previously that Newton's second law can actually be written in terms of momentum. It originally was written in terms of momentum. So the familiar force net is equal to mass times acceleration is actually a special case of the original nomenclature, which was force net is equal to a change in momentum with respect to time. So force is dp dt. And you can see, as we showed before, that if you put in the definition of momentum and assume that mass is constant, then we get our more classic form of ma right back out. Okay, and the next thing we covered was the, you might call, reverse of Newton's second law, which is that if f is dp dt, then the inverse of a derivative is a integral. And so the integral of force over time would then give us the change in momentum. So change in momentum would equal to the integral of force net dt from initial to final time, and that gives us a total change in momentum, which we give the special name of impulse, right? And this is sometimes called the impulse momentum theorem. Okay, so let's move ahead. The example that we would like to tackle is a soccer player kicking a ball, initially at rest, with a velocity of 20 meters per second. So the ball is going to fly at 20 meters per second after it's been kicked. The mass of the soccer ball is 0.45 kilograms, regulation soccer ball, and the impact between the foot and the soccer ball lasts for a duration of 50 milliseconds, or about 0.05 seconds. So let's calculate A, the change in the momentum of the soccer ball, and B, the average force applied to the ball by the foot. All right, so let's take a step back and look at what the strategy here is. So first of all, let's visualize what's happening. Soccer ball is sitting there perfectly stationary. It has no momentum. Something comes along and gives it a nice swift kick, and the soccer ball gets, it goes flying at 20 meters per second. So now in the final condition, it has momentum because it has mass and velocity. And so there's been a change of momentum from 0 to this finite value. So for A, where we're asking to calculate that change in momentum, clearly what we're going to need is to use the definition of momentum, which is mass times velocity. And we're going to assume here that the mass of the ball doesn't change at all, so that a change in momentum is really just equal to the change in the velocity times the mass. Okay, for the second part, where we're going to ask about the average force applied, well, now we need a relationship between force and momentum, right? Because we've just calculated the change in momentum, and we would like to know the force applied. So that gives us back to either Newton's second law in terms of momentum, or the inverse of that, which was the impulse momentum theorem, right? Where we saw that the impulse, which is a change in momentum, is related to the force applied over a certain amount of time. Okay, so let's start with part A. So the solution to part A is very straightforward, right? The change in momentum is just equal to the change in the definition of momentum, being mv, but we assumed that mass of the soccer ball doesn't change, and so we can pull that out front and just make it m times the change in velocity. So we are basically looking at the mass times the difference between final and initial velocities. Okay, so we just can, at this point, just plug in numbers: 0.45 kilograms times 20 meters per second, final velocity, minus 0 meters per second, initial velocity. And plugging those numbers into a calculator, we get 9 kilograms meters per second. All right, so that's it. We've calculated the change in momentum. Part B, what we're going to do is we're going to make use of something else we talked about in the past, which was that the when you impart a force on something, of course, the force may vary over time, right? When I mentioned in class, as the toe first comes in contact with the ball, the amount of force being imparted onto the ball may not be the same as when you've reached full contact, where the ball, your toe is now fully pressed up against the toe. So uh, the details of the force may vary with time over that 50 millisecond application window, but the momentum change is equal to the net impulse, which, if you remember, is the area underneath the curve. So even if the impulse, even if the force changes as a function of time during this, let's say this is that 50 millisecond window, from first contact to when the ball completely leaves contact with your toes, the details are not important if what we care about is a change in momentum, right? Because the total change in the momentum was the area underneath this curve. And what we will do is we will replace this odd-shaped curve with a rectangle, which has the same area underneath the curve, right? And that means that the total momentum will just be that average force times the total duration, okay? So replacing the curve with a constant f applied over the entire impact duration will yield the same change in momentum. And that's what we care about, because the impulse momentum theorem tells us that the net impulse, the net change in momentum, is equal to the total integrated force over that area, over that time, right? So that's the integrated area. So that's going to be equal to, in our simplified version, the average force times, so this average force times the total time window, which gives us the area of this rectangular box. All right. So the change in momentum is the force average times delta t. And we already, so if we want to now calculate, we've got to go back and remember, what are we trying to calculate? We're trying to calculate, our goal is to calculate the average force applied to the ball, right? So the force, the average force here would then be equal to delta p over delta t, just rearranging the second half of this equation, right? Solving for average force. And that allows us to plug in numbers, because just previously we calculated what delta p was. It's 9 kilograms meters per second. And we divide that by the now full time window, and we get 180 newtons as our final answer. All right. Let's move on now to the concept of momentum conservation, which we've already discussed in some detail. So we've seen from Newton's third law, which holds true for any interaction between two objects, gives rise to a statement of the conservation of momentum. And you should go back in your notes if you're unfamiliar and see that starting from Newton's third law, we were able to with about 3 or 4 lines of math, come to a result that said that the total momentum is constant for any isolated system. So there really should be a note here that says for an isolated system. And what that just means is that if we define our system broadly enough so that we encompass all the things that are interacting in that system, then the total momentum of the system will be conserved. Right? Now, remember that momentum is a vector quantity of motion, so that it has a direction. And as we've seen with all things that are vectors and all things that have direction, we know that the motion along orthogonal axes are independent. So if we define a set of axes, an x-axis, a y-axis, a z-axis, that are perpendicular to each other, right? So that each axis points 90 degrees relative to the others, then we know that motion along one axis does not affect motion along the other. So what it says is, if momentum is a vector quantity and momentum is conserved, then momentum along each axis also must be independently conserved. So if you take the sum of the x component of the momentum in each of all the objects, and you sum them up in an isolated system, that will remain constant. If you take the y component of all the momenta in a system and sum them up, they will be constant. If you sum up the z components of all the momenta in a system, they will be constant, right? Which is to say that the final momenta in a system in the x component is equal to the initial x component of the momenta of the system, right? Now, these three constants are not the same constant, right? Something can have a zero x component, but have a non-zero y component, right? If something is, if we've got two objects that are moving purely in the y direction, one's moving in the positive y, one's moving in the negative y, let's say, or let's say they're both moving in the positive y, then they both have positive y momenta components, but because they're not moving in x at all, they have zero. So in that case, this constant would be zero, but this constant would be something positive, right? Okay, so it's time now to do something interesting. Now that we've talked about all the momenta of various objects and talked about being able to change momentum, we are at the point where we can talk about things colliding, right? Objects interacting with other objects, which we've already started to a little bit, but we're now going to be very explicit about the types of collisions we're going to look at. So there are, in general, two types of collisions we can talk about. There are elastic collisions and there are inelastic collisions. And what we want to be careful here, because it confuses a lot of beginning students. It confuses a lot of senior students too, because it's one of those cases where the word elastic and inelastic in English is used in a slightly more loose sense than what we use it to mean in physics. Elastic in physics does not just mean deformable, even though we sometimes use it that way in English, right? We might say that he's got an elastic memory, meaning it's very malleable or something, but it's not a proper use of the word elastic in the physics domain, right? Perfectly fine way of using it in English, but in physics, we have a more precise definition for elastic. And in physics, the definition elastic really means that it restores its original shape after deformation, right? Examples of things that do this are, of course, springs, but also things like rubber bands. Anything where if you push on it, it may deform, but deformation by itself is not enough because clay would deform, right? But clay is not elastic. Clay doesn't bounce back. Anything that will restore its original shape as soon as you remove the force that's deforming it, that is elastic by a physics definition. And in contrast, anything that stays deformed after the deforming force is removed, for instance, clay, would be considered inelastic. All right, so the types of collisions, there are, again, two types of collisions, but there's really kind of a third class that's kind of in between. So one class is the perfectly elastic collision. Many times people just refer to them as elastic collisions, leave out the perfectly. So if somebody says an elastic collision, it's assumed to be a perfectly elastic collision. An elastic collision is a collision with no kinetic energy being lost. Kinetic energy is conserved in a elastic collision. One of the hallmarks of an elastic collision is that the two objects separate undeformed after the collision. So you have two objects coming in, they collide, and after the collision, the two objects go their own independent ways, right? And they are undeformed compared to how they were before the collision, right? A very classic example of this would be two very hard metal spheres coming in, knocking off of each other, and flying off in their own directions. And the metal spheres are assumed to have not gotten dented in the process. Let me jump ahead and look at the perfectly inelastic collision. So the perfectly inelastic collision is a collision in which the objects completely stick together after the collision. Right, so if you have two balls of clay that are sliding along some ice and they slam into each other and then they squish together and stick, right? Then that would be a perfectly inelastic collision. the objects deform and some of the kinetic energy is lost. Not necessarily all of it, right? Because these two blocks are moving in, not exactly opposite directions, or if there were two blocks moving in opposite directions and one was much bigger than the other or moving much faster than the other, then when they collide, it won't necessarily just stop and sit there. The combined mass, this merged double block of clay, can move together, right? But they would stay together because they're stuck together. Now that we've looked at the two extreme cases, the perfectly elastic collision and the perfectly inelastic collision, let's look at the intermediate case. The intermediate case being what's called a partially inelastic collision. In a partially inelastic collision, some of the kinetic energy is lost, so kinetic energy is not conserved, but the objects separate after the collision with some deformation. So what's happening here is an example of this might be a automobile accident where the two cars end up flying apart after the crash, right? They bump into each other and they fly apart. The collision is not a perfectly inelastic collision, because by definition, a perfectly inelastic collision, the objects stick together. But in this case, the cars kind of flew off, they bounced off each other to some degree. But because when they crashed, they did not retain their original form, right? The metal crumpled, so the cars end up damaged. In that case, it's not a perfectly elastic collision because they do not separate undeformed, right? If they had separated undeformed, the kinetic energy would be conserved. But because some of the energy actually went into crumpling up that metal, some amount of that kinetic energy is lost, right? So it's an intermediate case where kinetic energy is lost, but the objects do separate. Before we delve into the examples of different collisions, one more definition to be clear on. In general English, the word collision itself implies two or more objects crashing into each other with great force. But in physics, collision refers to any event, that should be event, in which two or more objects apply a force to each other over a relatively short duration. And that's regardless of the magnitude of the force. So it doesn't have to be a great force. As long as over the scale of the entire observation that you're looking at, the interaction was relatively short over that time scale, then it qualifies as a collision in physics. So a bowling ball striking a bowling pin, that constitutes a collision, but so does a flea landing on a leaf, right? Even though the magnitude of the force is very small, we can still treat the action of a flea landing on a leaf as a collision and use the same mathematics. Okay, so let's take a look at inelastic collisions. In a perfect inelastic collision, two colliding objects stick together after they collide. So before the collision, the system is characterized by two separate masses. So here in this illustration, I have a mass 1 and a mass 2, and I've used pictures of sticky buns because we're going to have them stick together, right? So we have two blocks or sticky buns, and one is moving in one direction and the other is moving the other direction, right? But before they collide, they're characterized by two individual masses and two individual velocities. After the collision, on the other hand, the system is characterized by a single combined mass with a single velocity. Because they've now stuck together, you can conceptualize them as a single mass. And of course, that mass is going to be m1 plus m2, right? Again, in all the experiments that we're going to be looking at, we're going to assume that the mass is conserved, meaning that we don't suddenly lose mass or suddenly gain mass out of thin air. Okay, so because it's an inelastic collision, in a perfectly inelastic collision, kinetic energy is not going to be conserved, right? That's part of the definition of an inelastic collision. But momentum for an isolated system is always conserved. For any isolated system, momentum is always conserved. So the question is, have we defined an isolated system here? And the only things that possibly interact, are the two sticky buns and the surface on which they're sliding. But if we assume that the surface is frictionless, then we only need to consider the two sticky buttons. There's no hockey stick coming in here, knocking one into the other, or a baseball bat, or some hand pushing. We don't. There's nothing else that changes anything about the system, uh, except possibly the floor. But we're going to assume that to be frictionless, and so it applies no force. Right? So in this case, the two sticky buttons by themselves constitutes an isolated system, and so momentum of the two sticky buttons together must be conserved. Both, so they have to have the same total momentum before and after. So the total initial momentum of the system has to equal the total momentum of the system at the final condition. Oops, I screwed up. All right, that's better. So the total initial momentum of the system has to equal the total final momentum of the system. The initial condition is you have two separate masses with two separate velocities. The momentum initial total is m1v1 plus m2v2, whereas the total final momentum will be the m combined, which is just going to be m1 plus m2, times that single combined velocity. So now let's take a look at some strategy. First thing to do is, of course, we want to visualize what's going to go on, right? What's going to happen. So we have a block moving in this direction, another block of a different mass moving in this direction, and the first mass is a 10 kilogram block. The second one is a 5 kilogram block, so this one's more massive. Then the velocity for the first block is 4 meters per second, and the velocity for the second one is 2 meters per second. So this one is bigger and moving faster, and this one is smaller and moving less quickly. So this one has a larger momentum than this, right? Since both its mass and its velocity are larger than this one's mass and velocity respectively, there's really no other conclusion to reach but that this has more momentum than this one and oriented in the opposite direction. So as they slide towards each other, they'll get closer and then they'll crash into each other. And it makes sense that if you think about a large, fast-moving object crashing into a small, slow-moving object, that it's the fast, large-moving object that's going to win. So intuitively, we have a sense that the final velocity is going to be going in the same direction as that bigger mass. How fast it's going to go, we'll have to calculate. But just as an initial guess as to a visual image of what's going on, the two blocks come in, they collide with each other, and then the stuck together masses will probably slide off to the right. Okay. So again, we have to choose whether we want to define an isolated or a non-isolated system. The next thing we need to do is then define what our system will be. We'll choose a coordinate axis. We'll need to define, then once we have kind of an idea of all that's going on and a coordinate system, we go back and define what it is we're trying to calculate. And then finally, we want to decide what concepts, what laws, what tools we have that will help us achieve our goal. All right, so let's take these strategy steps one at a time. We've already kind of made a visualization of what's going to go on. They're going to come together and then they're going to stick together and move off probably to the right. We need to define or decide upon whether we want an isolated or non-isolated system. So in this case, what we're trying to find is information about the final state. We're not given information about the final state. We're only given information about the initial state. Initially, it's a 10 kilogram block moving with 4 meters per second this way, etc. Right? So in order to relate the initial state to the final state, we typically want to use some sort of conservation law. Right? Which means in this case, we want to use conservation momentum. Right? We know we can't use kinetic energy or conservation of kinetic or mechanical energy because since they stick together, some energy, kinetic energy, gets lost in the deformation of the two buttons, the two blocks. So kinetic energy is not conserved, but momentum always is if we have an isolated system. So it makes sense that we're going to want to try and define an isolated system in this case so that we can use the conservation of momentum to compare before and after. All right? So without friction, and it's stated in the problem that we are moving on a frictionless surface, the two blocks together alone constitute an isolated system because there's nothing else coming in to manipulate the system. Again, nobody pushing, no hockey sticks coming in, slapping them, or anything like that. Just out of convenience and convention, we'll choose the positive x-axis to point to the right. And this is a one-dimensional problem, so that's pretty much all we need to do. We want to, the next thing is to consider what is our goal, right? Our goal is that we want to characterize the motion of the combined mass after the impact, right? We want to know its velocity. How do we reach this goal? What tools do we have to use this? Well, this is an inelastic collision because the blocks stick together. That means, as we just said, kinetic energy is not conserved. But we have defined an isolated system, so momentum is conserved. So we're going to make use of conservation of momentum, right? And the statement of conservation of momentum is that the sum of the momentum all the objects beforehand equals the sum of the momentum of the objects afterwards, but in this case, there's only one combined object. Okay, so let's go ahead and solve this. Starting with the equation we just said, we are trying to solve for the velocity of the object in the final state. So I just highlighted that as the thing we're trying to solve for. We can replace m combined, the mass of the combined object, is just mass 1 plus mass 2. A little bit of algebra, bring the combined mass down to the bottom of the other side, and we arrive at this equation. The velocity of the combined object is mass 1 times velocity 1 plus mass 2 times velocity 2 over the sum of the masses. So now all we have to do is plug in numbers, and we get that the combined velocity of the combined object is going to be 10 times 4 plus 5 times minus 2, right? And here's the key, is that remember that velocity is a vector. Even though it's a one-dimensional vector, it still retains its direction in the terms of the sign of this speed, right? So this thing actually is because it's moving in the negative x direction, has a minus 2 meters per second velocity, right? And so it's important to keep track of those signs. And that's why it's important to always label your axis so it becomes clear that, oh, this one's pointing in the opposite direction and it's pointing in the negative direction. That one's the one to have a negative velocity. Right, so then we end up with what effectively is 30 kilogram meters per second over 15 kilograms, which gives us 2 meters per second as our final answer for the combined velocity, or the velocity of the combined object. All right. So now we can move on to elastic collisions. So in an elastic collision, two objects collide without any loss of kinetic energy. The objects separate after the collision, as pictured here, right? So they come in, they collide with each other, but then afterwards the two masses go their separate ways. Before the collision, the system can be characterized as two separate masses, right? Mass 1, mass 2, each with its own initial velocity. And here we'll label it V1 initial and V2 initial, adding the initial tag, because now, since we're still going to have two objects, 1 and 2 in the final state, we need to maintain this nomenclature. So after the collision, the system is characterized by the same two separate masses, right? There's an assumption here that there's no exchange of mass, that some of this stuff doesn't jump over to this guy, right? M1 stays M1, M2 stays M2, and they go their separate ways with their own separate final velocities, V1 final and V2 final. Now, in an elastic collision, both kinetic energy and momentum are conserved, right? And so we'll write out the conservation of kinetic energy and the conservation of momentum in terms of the variables, right? 1/2 mv squared for the first mass in the initial state, for the second mass in the initial state, for the first mass in the final state, right? Again, masses stay the same. And for the second mass in the second state, 1/2 mv2 final squared. The conservation of momentum in this case is also straightforward. It's just mv1 initial plus mv2 initial, m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. If we're given the initial velocities and the initial masses, and the masses stay the same, then we basically have two equations, 1, 2, with two unknowns, right? Because since the masses are assumed to stay the same, the only things we don't know are v1 final and v2 final. So we have two equations with two unknowns, so we should be able to solve this with algebra, linear algebra. And it takes about a page of math to do so. Not really worth going through that entire process here. It's in your textbook. It's in many textbooks. You can look it up if you are interested. You won't, of course, not expected to rederive any of that, and in fact, you really won't even be expected to use the results. I'll give them to you, but this is kind of in the plug and chug regime, right? If you're given the masses and you know the initial velocities, all of you can take time to plug a whole bunch of numbers into calculators and get the right answer. It's really not the point to try and do all this. It's more important to understand, maybe for some special cases, how we might go about doing something like this. All right. So I think in your homework, there's not very many cases of elastic collisions, and if there are, I don't ask you to completely work it forward because it usually involves a quadratic equation and you have to solve for it. It's a lot of math. I think our time is better spent on other things. So one type of question that you might be asked to is to verify, right? And verify that a result that's given would be legitimate, right? And there it's stressing more the concepts. So can you verify that for let's say a block of mass 10 kilograms sliding to the right along a frictionless surface at 2 meters per second towards the second block, which is lighter, 5 kilograms, sliding in the opposite direction at 4 meters per second, this time the smaller one going faster. Assume that the resulting collision is perfectly elastic. Can you verify which of these choices of final velocities would be consistent with a perfectly elastic collision between these two blocks, right? And so rather than working forward to a solution, can you go from a solution, work back and make sure that one of these solutions and only one of these solutions will work, and conserve all the things that are supposed to be conserved, right? So let's go through it. What do we know about elastic collisions? Elastic collisions, according to our previous slide, has both conservation of kinetic energy and conservation of momentum. So what we can do is we can just go through, in this case, each of these cases by hand. And I mean, one way you could do it is you could take these numbers and plug them into these equations, right? But that's a lot of math. Let's see if we can do this in a slightly more intuitive sense. Okay, so let's consider option A. Option A says that the initial velocity of the first one and the initial velocity of the second one are 0, right? So they're just, the final velocities are 0, which means that after they collide, they just sit there, right? So what we should do is let's calculate the momentum and the kinetic energy of the system in the initial state, right? We know that we need to conserve both for an elastic collision. So let's calculate them so that we have something to compare to. The total momentum in the initial state is going to be m1, 10 kilograms, times v1 initial, 2 meters per second, plus the momentum of the second block, which is m2, 5 kilograms, times the velocity of the second mass, which is minus 4 meters per second, again, because it is moving in the opposite direction and moving to the left. And here I should have put a positive x. And I'm going to go ahead and stop and do that. All right, that's better. All right, so minus 4 meters per second because the velocity of this one is pointing the opposite direction as the positive x. All right, and so that gives us 20 plus minus 20, which is 0. So after we've done the math, we've seen that although this one has momentum moving in the positive direction, this one has momentum moving in the negative direction, the total momentum of the system in this initial state is 0. And we can see that from scaling that makes sense because this one is twice the mass of the second block, but the second block has twice the speed of the first block. And in momentum, everything is linear, so the two momenta cancel out. The two have equal momenta, equal and opposite momenta, and they cancel. All right, so we have 0 initial momentum. Let's take a look at their kinetic energies. So here, kinetic energy is 1/2 mv squared plus 1/2 mv squared for the second block. That would be 10 times 2 times 2, which is 4. And here it would be 5 times 4 times 4, each one times by 1/2. That gives us a total of 60 joules. This one being 4 times 10 is 40. Half of that is 20. This one is 16 times 5, which is 80. Half of that is 40. So the 40 plus the 20 gives us 60. So we have 60 joules of total kinetic energy in the initial state. So now let's go back to our 4 choices for answers. If we look at the first choice, the total momentum of this option is 0 kilograms meter per second, right? Because the final velocity of this first one and the final velocity of the second one are both hypothesized to be 0. And in this case, the total momentum would be 0, which matches what we know to be the total initial momentum. So far we're looking pretty good. But if we calculate the total kinetic energy in the final state, we find that it is also 0 joules, right? Because nothing's moving. But we know that for an elastic collision, kinetic energy is supposed to be conserved, and since it started with 60 joules, it's supposed to end with 60 joules, so clearly this is not the right answer. Let's move on to B. B, if we calculate the momentum of the initial state, we have the momentum of the first block, which is now posited to be moving in the negative direction with 1 meter per second. So minus 1 meter per second times the 10 kilograms, plus the momentum of the second block after the collision, which is now posited to be also moving 1 meter per second in the negative direction. So this is a case where we thought maybe they came together, but they ended up this one going this way and this one going that way. In this case, they actually didn't even separate, right? So they basically stayed together and moved in the same speed and direction. But as you can see, just from momentum considerations, that gives it a negative 15 kilogram meter per second momenta, total momentum, which is not 0, right? So that doesn't match even from there. We could calculate kinetic energies, but there's no need at this point. So let's move on to the next one. I'm going to just go ahead and jump down here to D, because I know it's also a wrong answer. We calculate the final momentum of option D, where let's take a look at what option D is. D is saying that after the collision, both blocks move in the positive direction, but the smaller block bounces off and goes faster. But this one continues to move this way, maybe a little bit slower. Let's see if this is consistent with it being an elastic collision. Final velocity of 1 meter per second on the first block gives us 10 times 1. And here we get 5 times 2 for 5 kilogram block moving at 2 meters per second. So that's 10 plus 10 is 20. Again, that is not equal to 0, so there's no need to go any further. We know this is not consistent. But for block C, for option C, where we say we think that the first block is going to bounce off and end up going 2 meters per second backwards in the negative direction, while the second block is going to bounce off in the positive x direction at 4 meters per second. Right, let's see if that scenario works out. Well, it's 10 times minus 2, which is minus 20, plus 5 times plus 4, which is positive 20, and that cancels out to give us 0 kilograms, kilogram meters per second. So from a momentum standpoint, we have conservation of momentum. It's consistent there. So now we move on to the next stage and we say, what's kinetic energy? Well, kinetic energy is 1/2 mv squared. So that's 4 times 10 is 40. Half of that is 20, plus 16 times 5, which is 80. Half of that is 40. So again, we get 20 plus 40 is 60. And so it's completely consistent. So that's the right answer. The two bounce off with the exact same initial velocity, final velocities as their individual initial velocities, but they end up having opposite directions. Now that is not the general case for elastic collisions, but it happened to be the case because in this case it had a 0 total momentum.